Good evening, sir. This night, I'm gonna present to you the uh, working principles of four-stroke and two-stroke engine. So first, I'm gonna start with the four-stroke engine. So what is four-stroke engine? Four-stroke engine, also known as the four-cycle, is an internal combustion engine in which the piston completes four separate strokes which comprise a single thermodynamic cycle. A stroke refers to the full travel of the piston along the cylinder in either direction. The four separate strokes are termed number one, intake, number two, compression, number three, power, and number four is exhaust. So first, what is intake? So intake, this stroke of the piston begins at the top dead center. The piston descends from the top of the cylinder to the bottom of the cylinder, increasing the volume of the cylinder. A mixture of fuel and air is forced by atmospheric or greater pressure into the cylinder through the intake port. So number two is compression with both intake and exhaust valves closed. The piston returns to the top of the cylinder, compressing the air or fuel-air mixture into the cylinder head. So number three is power. This is the start of the second revolution of the cycle. While the piston is close to the top dead center, or what we called TDC, the compressed air fuel mixture in a gasoline engine is ignited by a spark plug in gasoline engines, or which ignites due to the heat generated by compression in a diesel engine. The resulting pressure of the combustion of the compressed fuel air rather mixture force the piston back down toward bottom dead center, or what we called BDC. So last is the exhaust. So during the exhaust stroke, piston once again return to top dead center while the exhaust valve is open. This action expels the spent fuel mixture through the exhaust valves. So in this video, I'm gonna show you the design and engineering principles here. So here is the power output limitations. So like what I've said earlier, the four-stroke cycle are intake, compression, power, and exhaust. So number one is the by the way, A is in this picture above my head is you can see the design and engineering principles of the four stroke. So you can see there the green is A, the orange is B, the red is C, and the D is blue. So A is intake, B is compression, C is power, and D is exhaust. So number one is the TDC, or what we call the top dead center. And the next is number two is the BDC, or what we called the bottom dead center. So the maximum amount of power generated by an engine is determined by the maximum amount of air ingested. The amount of power generated by a piston engine is related to its size or cylinder volume, whether it is a two-stroke or four-stroke design, volumetric efficiency, losses, air to fuel ratio, the calorific value of the fuel, oxygen content of the air, and speed. The speed is ultimately limited by material strength and lubrication. Valves, pistons, and connecting rods suffer severe acceleration forces. At high engine speed, physical breakage and piston ring flutter can occur, resulting in power loss or even engine destruction. Piston ring flutter occurs when the ring oscillate vertically within the piston grooves they reside in. Ring flutter comprim- comprises, compromises the seal between the ring and the cylinder wall, which causes a loss of cylinder pressure and power. If an engine spins too quickly, valve springs cannot act quickly uh, enough to close the valves. This is commonly referred to a valve float, and it can result to a piston to valve contact, severely damaging the engine at high speeds, and lubrication of piston cylinder wall interface tends to break down. This limits the piston speed for industrial engines to about 10 milli per seconds. So, intake or is exhaust port flow. So, the output power of an engine is dependent on the ability of intake air-fuel mixture and exhaust matter to move quickly through valve ports, typically located in the cylinder head. To increase an engine's output power, irregularities in the intake and exhaust paths, such as casting flaws, can be removed, and with the aid of airflow bench, the radii of valve port turns and valve seat configuration can be modified to reduce resistance. This process is called porting, and it can be done by hand or a CNC machine. So next is supercharging. One way to increase engine power is to force more air into cylinders, so that more power can be produced from each power stroke. This can be done using some type of compression device, also a supercharger, which can be powered by the engine crankshaft. Supercharging increases the power output limits of the internal combustion engine relative to its displacement. Most commonly, the supercharger is always running but there have been designs that allow to be cut out or run at varying speeds relative to engine speed. Mechanically driven supercharging has the disadvantage that some of the output power is used to drive the supercharger while power is wasted in the exhaust high pressure exhaust as the air has been compressed twice and then gains more potential volume of the combustion, but it is only expand in one stage. And so next is the turbocharging. Though a turbocharger is a supercharger that is driven by the engine's exhaust gases by means of a turbine. If it consists of two-piece uh, high-speed turbine assembly with one side that compresses the intake air and the other side that is powered by the exhaust gas outflow. When idling at a low to moderate speeds, the turbine produces little power from the small exhaust volume. The turbocharger has little effect and the engine operates nearly in a naturally aspirated manner. When much more power output is required, the engine speed and throttle opening increased until the exhaust gases are sufficient to spin the turbocharger's turbine to start compressing more air than normal into the intake manifold. Turbocharging allows for more efficient engine operation because it is driven by exhaust pressure that would otherwise be mostly wasted. But there is a design limitation known as turbo log. So the increased engine power is not immediately available due to the need to sharply increase engine RPM to build up pressure and to spin up the turbo before the turbo starts to do any useful air compression. The increased intake volume causes increased exhaust and spins the turbo faster and so forth until steady high operation is reached. Another difficulty is that the higher exhaust gas to transfer more its heat to the mechanical parts of the engine. So next we are going to talk about the two-stroke working principles engine. So what is two-stroke? A two-stroke, uh, also known as two-stroke cycle engine, is a type of internal combustion engine that completes a power cycle with no stroke, with two strokes or up and down movements of the piston during one power cycle. This power cycle is being completed in one revolution of the crankshaft, while a four-stroke engine requires four strokes of the piston to complete a power cycle during two crankshaft revolutions. In two-stroke engine, the end of the combustion stroke and the beginning of compression two-stroke happens simultaneously with the intake and exhaust or scavenging functions occurring at the same time. Two-stroke engines often have a high power to weight ratio, power being able in a narrow range of rational speeds called the power band. Two-stroke engines have fewer moving parts than four-stroke engines. So that's the end of my presentation, and I hope that uh, I I presented it well, though my light is not so though my light is dim. So that's all my presentation, sir, and thank you for listening.